This is a continuation of more growth and decay. Writing functions and seeing functions in exponential growth and decay. Here's the next example. Let's look up here. Okay. Again, let's start at 0. That's the easiest. So when I substitute in 0 for x, I'll have 5 times 2 to the 0. 2 to the 0, of course, like everything that's to the 0, is 1, and 1 times 5 is 5. Of course not 0 to the 0, but we all know that. These other numbers will come in. Go ahead and work them out to make sure you get these values. And again, negative exponents do not result in negative numbers. It means reciprocal. How do I get from one to the next? Well, let's see, from 5 to 10, that's times 2. 10 to 20, that's times 2. Oh, look, it's times 2. Same deal down here. 2.5 times 2 is 5. It works each time. That is the base of the exponent. The base of the exponent is the factor that we multiply to progress to the next item. And look here. When x is 0, the y-intercept is 5. That's the point 0, 5. That's the y-intercept. 5. Notice that 5 is the number that's out here in front. Of course it's going to be, because whenever it's to the 0, you're going to be multiplying by 1. So you're going to get 5, and your intercept is going to be the number there. So when you have it, that's your intercept, and it's the one that's right there. So in the formula here that we're developing, it'll be the y-intercept. Let's look at the next one, see what happens there. 0 is the easiest one to start with, so I'll start with 0. This will be negative 2 times 4 to the 0. Again, 4 to the 0 is 1, so it's just negative 2. Again, that is the y-intercept, and it's right here in my equation. Why? Because anything to the 0, x is 0, anything to the 0 is going to be 1, except for 0. Anything to the 0 is going to be 1 times negative 2. It's just going to be whatever that number is. That is the intercept, the point 0, negative 2. The rest of these, make sure you can get these numbers. Will come out like this. Okay? So how do we get from one to the other? Well, from 2 to 8, negative 2 to negative 8 is times 4. Times 4. 32 to 128 times 4. Does it work down here? It does. Negative 1/2 times 4 is negative 4 over 2, which reduces or simplifies to 2. Same deal here. Negative 2. What am I doing? It's times 4. I wrote that wrong. There we go. Times 4 each time. And that times 4, again, is the factor that we're using, and it is the base of our exponent. It's the one. How many times do we multiply by 4? That's what the x is. Okay? So we're starting to see a pattern here, I hope. Here's the next one up. Now we're going to deal with those nasty fractions. Everybody's favorite. They're not so bad. And let's start with 0. That's just like the easiest thing to start with. So when I do this, this will be 1/4 to the 0 power, which is 1. Anything to the 0 power is 0, except 0. As you go through and check through these, you'll get these numbers. For example, here, this is 1/4 to the first power. This is 1/4 to the second power. 1 squared over 4 squared. Make sure you can get these numbers. Oh, looky there. How did that come up? I've got 1/4 to the negative 1 power. We remember that negative 1, a negative exponent, means reciprocal, so we take the reciprocal, lose the sign, we get 4. Same deal here. This will be 1/4 to the negative 2, the reciprocal, and then squared. Does it bear out here? Yeah, it bears out here. What do we multiply to get to each one of them? We multiply by 1/4 each time as we go along. Okay. Next one up. To the negative 1/5. I mean negative 1/5 to the x. I'm sorry. Same thing. We'll do this. Negative 1/5 to the 0 power. Okay, 1/5 to the 0 power is 1. Notice that the negative is outside the parentheses. It's not part of the number that is raised to the 0 power. Therefore, we do only the parentheses. 1/5 to the 0 is 1, and then we apply the negative. This is negative 1. Same thing will work on each one of these. Make sure that you can get these numbers, that you know how to do it. How do we get from one to the next? Well, we multiply by 1/5 times 1/5. Same as dividing by 5, but in this we like to talk about multiplying instead of dividing, but yeah, it's the same thing. So times 1/5 works all the way along. Again, the factor that we're multiplying by is 1/5, and that is the base of our exponent. Look here. What's out here? That's a negative 1, right? Yeah. The factor that's outside, that's multiplied by the base and the exponent, is negative 1. Look here. There it is. Negative 1 is our y-intercept. 0, negative 1. Same deal up here. The factor that's on the outside, there's something there. Even when it's not there, it's there, and it's 1. And that is our y-intercept. Let's look a little bit more here. We come to a pattern here, and here's the pattern. Okay? An exponential function, our formula, base formula for an exponential function in this case will be y equals ab to the x. A is the y-intercept, and b is the growth factor. That's what we're multiplying to do it. You remember in our previous examples with banking and decay and growth, we talked about that. The one that's raised to the power as being the factor. Here it's all put together. There it was in parentheses, and it was 1 plus or 1 minus. So this is our basic form for an equation of an exponential function. Let's look at what this looks like. We haven't done that yet. Here's one that's an example. Okay. Well, I want to write this one in an equation to see what it looks like. The basic form of the equation, as I just mentioned, is y equals ab to the x. Now remember, back from our lines and everything else we've done, if you have an equation of a line, or in this case of a curve, it will be true for every point on the line or curve. So any point I choose on this curve, its coordinates x, y, any point I can substitute into here, and it will be true. Okay, well, what do I know? I need to be able to write this equation. I need to know the y-intercept and this growth factor thing. Okay, well, I know the y-intercept. It's right there. So I can just put that in. You'll recall, when we use these standard forms of equations, we need to, when we're done, we want to have an x and a y, and everything else has to be a number. So that means this b has to go. It's got to go, and then we'll have the x and y left. But how am I going to make it go? Well, you know, I have this one point here. I know that point is actually on the line, and it's the xy of it is that. It's 112. I can use that one point. It's true for every point, so it's true for that point. So the y value is 12 equals 10 times, and then that 10 times b, which I don't know, sorry, 10 times b, that's what I'm trying to find out, to the x, and the x is 1. Then I just solve it. Divide both sides by 10. I'll get 10 over 12 equals b. I can write that as 1.2. I can write it as a reduced fraction as 6 over 5. Either one is just fine. Okay? So now I know what b is. b is 1.2, or 6 over 5, or 12 over 10. I can now put it back into my form along with the intercept, and then I'll have the equation of this particular exponential curve. So that's y equals 10 times 1.2 to the x. So that, friends, is the equation of this curve. A couple of things about this that we need to observe about it. Remember range and domain. Yeah, everybody's favorite. Domain. That's the x value. It's how far it'll go this way, how far it'll go this way. If I come all the way out here somewhere to x, or maybe to x is 2 million, will there still be a y value for it? Will it still be at the curve? Yes, it will be. The curve keeps going out as it goes up. It keeps going out as it goes up. So no matter how far I go along, there will be a value of the curve that matches up with the x. What about the other direction? Yeah, it's doing the same thing. It's slowing down, it's going lower, but it'll just keep getting lower pretty much and keep going to the left. There will always be an x value. So the domain then will be all real numbers. What about the range? The range is how far up or down the curve is, and where there'll be a value for it for y. Okay, well, everything up, it's going to keep going up. So we know it's got to be bigger. It's not going to have a top limit on it. What about the bottom limit? Look what we're doing here. Each time, going backwards, we're dividing by 1 over 2, going backwards. Dividing by 1 over 2, dividing by 1 over 2, dividing by 1 over 2. It's getting smaller, but please notice that if I divide by 1 over 2, or take 5/6 of it going backwards, times 5/6, 5/6 of the number is going to get smaller. Then 5/6 is going to get smaller, 5/6. It's never, however, going to actually go down to 0. So like if you have 5/6 of just the tiniest little bit, it's still not down to nothing. There's still something there. It never actually becomes 0, and it never actually becomes negative. You just got to kind of look at these as see. So what we can see is that y will always be greater than 0, not equal to 0, but greater than 0. Okay, let's try another one of them. We've got one. Oh, I forgot to tell you the other thing. The funny word. As the curve goes down, it's going to keep going up. There's no limit. But notice, like we just said, it's never going to actually be 0. It's never going to go negative. It will not cross the x-axis. The line that a curve will not cross is called the asymptote. Fun word. Words you need to know. A-T-O. Asymptote. That's an E. There you go. Asymptote. Sorry. The line that the curve never crosses is the asymptote. How did I get this one? I reasoned through and thought, what happens to the curve as x gets very, very small? As x gets very, very small, you're dividing and dividing and dividing, but you never get 0 and you never get a negative number. So I then understand that it will not cross the x-axis. The x-axis, the line it will not cross, is called the asymptote. Okay, next one up. Here's one that's going downhill. We're going to do the same thing. We want to find the equation for this function. We recall that the standard form is y equals ab to the x. A is the y-intercept, and b is the growth factor, or in this case, the decay factor, since it's going down. Okay. I know the intercept is 8, so I can just put that in. I know that every point on the curve, if substituted into the equation, will give a true statement. Every point on the curve will be true for the equation of the curve. I have a point on the curve. All I need is one, and fortunately I have one. So this is xy equals 1, 4. So I'll go ahead and put in 4 for y, substitute that in, equals 8 times b to the 1. Solve for b, because b is what I want to know. That'll give me 1/2 equals b. Now I know my growth factor. I'll go back to my original equation, put in the growth factor and the intercept, and I'll have the equation. Y equals 8 times 1/2 to the x. Again, when you have your equation from a standard form, you must still have the x and the y, but everything else has to be a number. Okay, let's evaluate. Are there asymptotes here? Yes, there are. Let's think about it. The same argument we just made. Here, you're multiplying by a half. Times a half, times a half, times a half, times a half. Now, that gets really, really teeny, really, really quick. But as long as you've got something and you take half of it, you still have something. You don't have nothing. It's not going to never be 0. No, 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 no. It's not going to cross this line. So we know that it's not going to cross the line. This will be the asymptote. And the equation of this asymptote is y equals 0, because it's the x-axis. Let's look at the range and the domain. The range is the the up and the down. It's the y. What can the y actually be? As we've just described here, the y can be all positive numbers. So the range is y is greater than 0. Because remember, taking half and half and half and half, you're never going to get to 0, so it can't be equal to 0. What about the domain? The domain, as you'll recall, is what the x value could be. Is it going to keep going that way? Yeah, it's going to get really tiny, but it's going to keep going that way. There will be a value for x no matter how far you go. What about over here? It's going to get high really fast, but it's going to keep going out. It's going to keep going out. It's going to be a really big number when it goes out, but there will be a number there. So we can see that for every value going to the left or to the right for x, there will be a value. So the domain is x is all real numbers. To show you a little explanation on that, kind of a summary here. We've got them going up, we've got them going down. So AB to the x, A is bigger than 0, that's exponential growth. Exponential decay is when A is still bigger than 0, still in the top, but the difference in it is the B. Here the B is bigger than 1 and it's increasing. Here the B, or the growth factor or decay factor, is between 0 and 1. It's a fraction. If it's a fraction, it's going down. Let's think about that. You multiply by a half, then you multiply by a half, then you multiply by a half. That's going down. That's decay. Over here, it's a number that's bigger than 1. You multiply by 2, then you multiply by 2, then you multiply by 2. It's getting bigger. So exponential growth and exponential decay is what we call it when it's here in the first and second quadrant with these criteria. I'm going to do some examples of graphing exponential functions here. One that we just did was y equals 3 to the x. So we'll see what that looks like to graph it. Okay. We can graph it with all the different points. That's one way to graph. So how would I do that? I would look at this and say, okay, at 0 it's 1. At 1 it's 3. At 2 it's 9. And at 3, it's already off the chart. Okay, go back the other way. At -1, it's a third, pretty little. -2, it's a ninth. I can't hardly even draw it. Then what I do at this point, you know, for real, if you're going to really be drawing an exponential curve, you're going to use some kind of plot or some kind of computer to do it. For our purposes, all you need to do is recognize what an exponential curve does. It starts little bitty, little bitty, little bitty, and all of a sudden goes up. So when you draw it, just kind of draw it along like this and make it go up really fast. And that's good enough. How could we do this based on just the equation? We know that the intercept is 1 because that's the a that's not there, so it must be a 1. Then we can choose any other point. This will tell, we know from looking at it, it's positive that it's going to be in this quadrant and it's going to go up. We'll talk about the negatives here in a minute. So it'll start out here and then whoop, go up really fast. We just need one other point to know how wide to draw it. So really all I needed to know was the intercept and one point. And then I just kind of fudge in a line that looks like an exponential curve and I'm done. Okay. The next one up. Let's do one of the negative ones. -2 times 4 to the x. This is one of the ones we worked earlier. Graphing it on points, we would do the same thing. But notice what's going to happen to this one. It's going to go down. Notice that the negative is what does that. So if I start my intercept, is going to be 0, -2. The next one will be 1, -8. And I'm already off the chart down there. For -1, it's -1/2. Then it's -1/8, and it doesn't take me very long. I can't even count it because of the tools that I'm using. We'll do the same thing again. We'll just kind of make it go through that. Understand it's never going to actually be 0, and then it's got to go down like really fast. What makes it go down is the negative. That means it's in the third and the fourth quadrant instead. We don't actually call these exponential growth and decay, but they are exponential functions. Okay, so it's negative, so it's the mirror image. This one swooped up, this one swoops down. The intercept is changed because of the a factor, and then we're done. Could we do this without plotting the points? Sure. We'd have the intercept and one other point. We know that it's negative, it's going to be going down, so we just swoop it in using the 2 points. That tells us how wide or how quickly it goes down. Let's do a couple more of them here. Okay. Y equals 1/4 to the x. What's that going to look like? Okay, well, what's my a? Remember, y equals ab to the x. My a has to be 1, which means my y-intercept will be at 1. Then I need one more point. Okay, well, I had that here. How about another one? I like that one better. -1. This is our calculations that we did from before. So let's try, there's 0, 1, and I can just plug it in to get it. That's what I did before, right? So if I want to know at -1, I'll plug in, substitute -1 for x, and then I'll have just what we did before, which is the reciprocal of 1/4, which is 4. So to find out another point from the equation, input the x to find out the y. So -1, 4, -1, 4. And then -2 is already off the chart, I think. Yeah, okay. So, but that's really all I need to be able to do it. I have my intercept and my 1 point to know how quickly, in this case, it goes down. I know it goes down because it's a fraction, so I'm multiplying by 1/4 every time. It's going to get smaller, 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 smaller. I know it's in the top part of the graph in quadrants 1 and 2 because it's positive. The a factor is positive. So I just kind of swoop it down in here real fast, past those, and keep on going. And that's good enough. Okay? On this one. Now we've got the negative. It's going to be in quadrants 3 and 4, and we technically don't call it exponential growth and decay. What's the intercept going to be? Well, there's a 1 there. So the intercept is now -1. We can put that in. We need one other point to know how wide or how quickly it goes down. Let's get the easiest one. Here's our calculations from before. I'll use -1, -5, which gives us -5. Again, when I raise 1/5 to the -1 power for x to be -1, that means the reciprocal of 1/5, which is 5. The reciprocal 1/5 to the -1 is 5, and then put a negative on it. So that will turn out to be -5. 1/5 to the -1 is 5. The negative sign here is outside the parentheses, so it's applied after the exponent. That'll be -1, -5. And the next one's going to be -25, and it's already off the chart. This is exponential things. They go off the chart really fast. So we're just going to do the best we can. I'm going to say it's going to come up kind of like this. It's going to swoop around and go that way. And that's good enough. Okay. And here endeth the lesson.